All right, let's dive into it. Our first speaker of this final day is Tommi Muller from Oxford, who's going to tell us about hyperquiver representations and the Harder-Narasimhan filtration.
Okay, great. So thank you, Alistair, and as you were saying, and Cheryl for organizing the conference and for inviting me to speak. So today we're going to look at using geometric invariant theory, GIT, to study moduli spaces of hyperquiver representation. And these are hypergraph multilinear generalizations of quiver representations. So on the left here, you've got the Jordan quiver with one vertex and one loop. So this is you place a linear map on the edge here, but on the right you have a hyperquiver. So it has it's taking two copies of the vertex and mapping it to itself, and now we have a multilinear map going from the tensor product of the source with itself to the vertex. So these are the kinds of objects we're going to look at, and to put everything in context and go over the background we need, I'll just quickly go over just some GIT theory. So for our setting, we need affine GIT, so we're going to work over the complex numbers. And our setting is we have a vector space V on which a reductive group G acts linear. So the action is given by a representation rho like this. And we also have a G linearized line bundle over V. So this is a line bundle with an action of G on L, which is linear, and the projection map is G equivariant. So a fact in the affine GIT setting is that every G linearized line bundle up to isomorphism is basically of the form trivial line bundle, L equals B plus C, and G acts linearly on L by some character of G. So the character will twist the line bundle out. So every line bundle will look like this. So it's parameterized by the characters. And if G equals GLB, then we know that every character is of the form determinant to some power, which is given by the integer theta. And we call theta a stability parameter. And a point that's semi-stable with respect to this action we call theta semi-stable. So first we're going to look at semi-stability and instability from the level of points. So if V is a point in the vector space, we let CV be the set of one parameter subgroups for which the limit under the one parameter subgroup exists. Then we have this well-known criterion for determining when a point is semi-stable. So if we have a affine GIT case and L is listed by a character chi, then a point is semi-stable if and only if the pairing of chi with lambda is positive, and this is over all lambda for which the limit exists when it acts on B. So that's semi-stability. And what happens if a point is unstable? Well, we can, if we have some notion of how badly a point is unstable, so we have an inner product on the one parameter subgroups, which we're going to extend over Q. They become rational one parameter subgroups. Then we can measure the extent to which a point is unstable. So this is Kemp's instability here. If D is an unstable point, then you can find a rational one parameter subgroup that's unique up to positive scaling by Q and conjugation by the parabolic subgroup, which preserves the flag of lambda, which minimizes this function called the Kemp function. So
the problem with keeping an notation in my head was X is style G.
Oh, that's a set of one parameter sum. So it's a
Okay, and that would be PG.
sorry.
W sub PG.
Oh, that's the Weil group of G with respect to a choice on that choice. Yeah. So yeah, you can choose a maximal choice of G. Yeah. Yeah. So the CAN functional looks like this. It's the pairing over the norm with respect to the inner products. And then we minimize over the rational column of all one parameter subgroups for which the limit exists. If a point is unstable, then you can find a way in which it's maximally destabilized by some unique one parameter sum. So this is stability, semi-stability, and non-semi-stability at the point level. And then what does it look like globally? So where again the affine GIT setting L is twisted by character, and we have a inner product on the rational one parameter subgroups. Then we actually there exists a stratification of space V into a disjoint union of finitely many smooth, locally closed G-invariant subvarieties. And the first term in this stratification is the open set of semi-stable points. And all the points that aren't semi-stable, we have disjoint strata that are indexed by G conjugacy classes of minimizers of the count function. So yeah, so every point in the space therefore is either semi-stable or has some sort of instability type that's given by the maximally destabilized one parameter sum. So this is known as the HKN stratification of the space. And basically what GIT traditionally does is it just takes the semi-stable locus and throws away all other points. So it throws away all points in these other strata and takes the quotient of the semi-stable and set by degree G. And that's the GIT quotient. But in some sense, you throw a lot of information that way, and the moduli problem is not complete unless you can somehow quotient the unstable strata. So this is the philosophy of non-reductive GIT, which is to complete this moduli program by quotienting the strata. And so you get moduli of not just semi-stable objects, but also unstable objects. And to do this quotient, you have to quotient by a non-reductive group. So, and this is what people study. So,
Not always non-reductive. You could solve the reductive proof and end up with this certification and the scale of fortune and scale of reductive, or is it always non-reductive?
I think it's possible for it to be reductive, but generally, you'll have to quotient by the universe. Yeah. So this is all the GIT background we need, and so now we can talk about objects. So what's a hyperquiver? It's a directed hypergraph with finitely many vertices V and finitely many directed hyperedges E. And basically every hyperedge has a finite tuple of source vertices, incoming vertices, and finitely many target vertices. And these are given by these source and target counts, S and T. And a representation of a hyperquiver it's defined somewhat analogously for quivers. Is you for every vertex V, you place a five-dimensional vector space WV, and on the edge you put a linear map from the tensor product of the spaces on the source vertices to the tensor product of spaces on the target. So hyperquiver representations, generalized quiver representations are just the case when every edge has exactly one income and one outcome vertex for all the edges. We have a lot of other objects that are encoded by hyperquiver representations. So this was a hyperquiver we saw on the first slide. One vertex and two copies of the source, and then the same vertex as the target. A representation is basically encoding an algebra. So if for the vector space A on this vertex, the multiplication map of the algebra is given by the edge. And if you want to draw other pictures, you can think about bialgebras. So now you can draw pictures of these kinds of algebra-like objects, and here you have a multiplication map in red and a co-multiplication map in green. And we don't assume anything else like associativity or commutativity or anything like this, the relations. Those will form an G-stable closed subschemes if you assume such conditions. So these are quite general.
So I'm struggling with the definition of hyperquiver.
Yes.
I was under the impression it's simply allow any number of edges, but that's not enough, right? Edges may merge, and it's important. So you have two edges, red and green.
Yes.
And they may merge, or they may split, right? That's
yes. I mean, you can have any number of vertices in the source and target. So it might split, it might converge. Yeah, you're allowed anything.
But those two, I mean, you're considering red and green are part of the same hyperquiver.
Yes, it's one hyperquiver. Yeah, one big hyperquiver.
So even if everything goes in the same place, you still get two different maps.
Yes, that's right. Yeah. So if you want a different map for every edge, then you just draw the same edge. Draw another copy of the edge. Yeah. So maybe you want an algebra with two multiplication maps, then you just draw a different copy of the edge. Yeah. So these are examples. Another example is if U is a Lie group and rho is a representation of U, that the differential from the Lie algebra of U to GL of V induces an action of the Lie algebra, the representation by just acting in this manner, given by the differential. And so we can draw this as a hyperquiver with two vertices, Lie algebra of U on one and V on the other. And here the red map is just the Lie brackets map, and the blue map is this action that we discussed. So these are the kinds of objects you would see in non-reductive GIT again. Because with non-reductive GIT, you usually have some unipotent group that's graded by a one-parameter subgroup, such that the one-parameter subgroup acts on positive weights on every piece of the grading of the Lie algebra. So here I haven't drawn the grading, but if we were, then we would just have more vertices, one for each piece of the grading, and then more maps going from piece I and piece J to piece I plus J. So if you study modular such representations, then you're parameterizing all the possible non-reductive GIT quotients. This is useful for that. And so the setup of our problem is we have a hyperquiver, we have a dimension vector, which is just the dimension of all the states on vertices. And this is our space of hyperquiver representations. So we assign to every edge one such multilinear map from the source to the target. And so this is our vector space V, and we have a group G acting on this space, which is a product of GLs, this space at every vertex, and it acts by conjugation. So you basically invert, it's sort of a multilinear conjugation. You invert at the source and uninvert at the target. So this is how G acts on the space. And just like we discussed before, every character of a product of GLs is just a product of determinants to some power theta B, where theta B is an integer. And so this time we have a list of stability parameters, theta. So lastly, we can choose some inner product on the one parameter subgroups. And for this talk, we can just make things simple and choose the Euclidean inner products. So that the pairing of pi and lambda agrees with the inner product of pi and lambda seen as elements beyond. Note that the inner product is G conjugation invariant, so it doesn't actually depend on the basis. You just, if you want to know the value of the inner product, you just pick a basis, do the Euclidean inner product, and then it's the same no matter what basis you choose. So we have everything set up for applying GIT, and to see how things play out, we should first look at the simpler quiver case. So what happens with quiver representations? So Q is a quiver and phi is a quiver representation, and you fix some stability parameters theta. You can define something called the slope of the representation as follows. So it's the inner product of theta with the dimension vector at the numerator, and then the denominator is the sum of the dimensions. So that's the slope of a quiver representation.
What is a theta B?
Oh, the theta are stability parameters.
No, I read that, but I mean, what is the stability parameter?
Because
Is it like a band?
yeah, so because we're just looking at quiver representations, which is, so there's no tensor particles.
Yeah.
And that is important. So it's to target, and then you still have a group of GLs acting, but yeah, again, without tensor particles. Yeah, so we're just for now looking at quiver representations and seeing how things play out. So you can say that a representation is slope semi-stable with respect to theta if all sub-representations with dimension vector d prime less than d, you have the slope of that sub-representations less than the slope of the original representation. So if that's true for all sub-representations, we say that the phi slope semi-stable. And this investigation and
In your definition of the slope, you don't use pi at all.
that's true, yes.
So how can
Well, sorry. The sub-representation has to preserve the image of phi. So you can't just pick any subspace. You need to pick a subspace so that phi of that subspace is contained in this subrepresentation. Yeah. So this was all kind of work that King did for slopes and slope semi-stability and Quiver representation. This King's criterion says that the Quiver representation is theta semi-stable in the sense of GIT, if and only if it is slope semi-stable with respect to theta. So this is how the Hilbert-Mumford criterion works before.
But again, this definition seems to suggest to me that you have two representations that are different but have the same dimension vector, and you do the stability parameter with the same for both, then one will be a stable, a semi-stable, if and only if the other one.
So there's.
It is to depend only on D and theta.
But you have to pick only sub-representation. So they have to preserve they have to be closed under phi.
Yes.
Yeah. So you can't just pick any.
Yeah, I can take how we know.
Yeah. So that's the semi-stability story. And again, we can ask the question, what about unstable quiver representation? So if you have an unstable quiver representation, then for that unstable quiver representation, there's a unique finite length filtration by sub-representations. And let's denote those the dimensions of the sub-representations by the dimension vectors. So that's the filtration is increasing. The length of the filtration is larger than 1. And this filtration is characterized uniquely by two properties. So the first is that every successive quotient representation, so if you have subrepresentation I and subrepresentation I minus 1, the quotient I mod I minus 1, which has this dimension vector, that quotient has to be slope semi-stable. So every successive quotient is slope semi-stable. That's the first condition. And the second condition is that the slopes of these slope semi-stable representations have to decrease, like this. So for every unstable representation, you have this unique filtration with these two properties, and we call this the Harder-Narasimhan filtration. Fine. So basically, if you note what the dimensions of all of these sub-representations are, then that gives you a sort of Harder-Narasimhan type, and that type is exactly the index in the Hesselink stratification, G conjugacy class of lambda. That's why that's the sense in which it's unique, and in the sense it's parameterizing unstable representations. So that's the Harder-Narasimhan filtration for quiver representations, and one would hope that you can generalize this for hyperquiver representations. But the problem you run into is that the category of hyperquiver representations is not available. So you can't take quotients like you do needed to define this Harder-Narasimhan filtration. So the problem we have is, how do you define the notion of Harder-Narasimhan filtration for hyperquiver representation when we can't take quotients? And the other question is, how do we define the slope of such a filtration? So these are the two questions we answer, and the approach that we're going to take is to revisit this Kemp function and see what we can do with it to define HN filtration for hyperquivers. So I have to present some definitions first. So in hyperquiver, we say that we say that we have acute filtrations. If we have two things, one, a decreasing sequence of rational numbers L1 up to Ln, which we should think of as weights, and the filtration of all of the vector spaces WV that's increasing as you increase the index of the weight. So you start with 0 and yes.
I think this is no longer indexing of the function carrying over the home of all ones which exists.
Yes, so
And I sound minimum nonsense even. Does that make it?
So Kemp's instability theorem guarantees that the minimum exists. And yeah, sorry, I left out that lambda is a rational one parameter. So there is still a comment. So those the sequence of weights and a filtration of all of the vector spaces by these weights. So that's acute filtration. And you say acute filtration is admissible for hyperquiver representation phi if for any choice of weights, which we write as this function I that assigns source vertices to some index of the weight space, any choice of weights at the source, phi at edge E needs to send those weight spaces into the span of the weight spaces at the target whenever this inequality holds. So the inequality says that the sum of the weights at the target is greater than or equal to the sum of the weights at the source. And we'll explain why you need this. So the explanation is that these are just translating what it means to be one parameter subgroup and one parameter subgroup for which the limit exists. So this definition of acute filtration is the same, just a retranslation of saying that lambda is a one parameter subgroup, again after conjugation by the parabola. And admissible acute filtration is just a retranslation for a one parameter subgroup up to conjugation for which the limit exists. So now we're kind of seeing where we're going towards. If we do have a maximally destabilizing one parameter subgroup for the Kemp function, then we can watch what happens as phi, the representation phi is sent to the limit under this maximally destabilizing group. And we call this point the associated rate of phi, G of phi. If we have lambda, we know that it will split the WV, the spaces of the vertices, into weight spaces, which we call GRK WV, split them into weight spaces. And how does why is the associated gradient compare to phi? If we list out all the components of the associated gradient, the components are an edge, a choice of weights at the source, and a choice of weights at the target. So we get a component of GR phi like this. Then all of these components are the same as those of phi, except when you have this strict inequality. So in our definition of admissible acute filtration, there was a greater than or equal to, but when the sum of the weights of the target is greater than its weight, the source, the component of the associated gradient is 0. So the limit basically zeroes out all the components of phi for which this inequality occurs. And what this inequality is basically just saying, again, the limit exists. So if lambda x by conjugation on phi, then you get some t to the power of sum of weights at the target minus sum of weights at the source. And that limit only exists if the target is bigger than the source. So that's the associated gradient. And so the question is, how do we actually go about finding this maximally destabilizing one parameter subgroup? So, I'm sorry. And you know, it's the set of non-zero components of the associated gradient by this curly brackets. So, right. So, how do we actually go about finding lambda? To do that, we make some observation about the Kemp function. So we notice that if we scale lambda by a rational number q, both the numerator gets a factor of q and the denominator gets the factor of q, and they both cancel out. So actually, the Kemp functional only sees the ray that's spanned by lambda. And that's the non-uniqueness in Kemp's instability theory. Now, together with the conjugation by the parabolic graph, the function is not seeing this the specific point on array, but the entire array itself. Mm-hmm. If we actually wanted to obtain a specific point, we can take a hyperplane and intersect the array with the hyperplane and get one unique point that way. So let's do that. So let's fix the hyperplane. Inner product of theta with lambda is -1, and fix the basis for the WB. Then what happens? Then the numerator becomes -1, and to minimize the Kemp functional, you have to make lambda as small as possible. So finding a minimum of the Kemp functional is the same as this quadratic program. So it's minimizing the norm of lambda subject to a hyperplane condition, and also the condition that lambda is admissible, that the limit exists. And basically, we account for this by writing ML is greater than or equal to 0, where M is this matrix that just counts the multiplicity of how many times the target hits weight space K minus how many times the target hits the source hits weight space K. And if you do M times L, you'll get that inequality of sum of weights at the target minus sum of weights at the source. So that's what we're doing here. So now we can try and solve this quadratic program. And how do we do it? There's a quadratic program. We can use something called the Karush-Kern-Tucker conditions. So these are called KKT conditions. And I'm stating it for quadratic program, but so let's say you have a quadratic program here. It's a bit more general. There's a linear term, some set of equality and inequality constraints, and we assume G is positive definite. Then point x star is the unique global minimizer for this quadratic program, if and only if there exists mu I and mu j, which are called KKT multipliers, such that the following follows. So the first is a stationary gradient. So there's some Lagrangian associated to the quadratic program, and it's saying that the Lagrangian, the derivative of the Lagrangian at x star is 0. It's a critical point. obviously XOR has to satisfy the constraints, so that's what we have here. Prime feasibility. We have a condition called dual feasibility, which is that the new j's have to be greater than or equal to 0. And this last condition called complementary slackness, which basically says that the inequality constraints are as tight as possible. So if we use this KKT condition, we will be able to define a notion of HN filtration. So if F is an admissible Q filtration with weights L1 up to Ln, we write dvk for the dimension of the kth weight space at vertex V, and then we just define these quantities which you've already seen. So the filtration F is represented by the one parameter subgroup lambda. So we define the pairing of theta with lambda as this. The norm of lambda squared is what you expect. dk is the sum of the dimensions of the weight space K over all of the resistance G. Theta is, so that's the numerator, sorry, that's the denominator of the slope which you saw for quiver representation. Theta K is the same thing, it's the analog of the numerator for the slope of quiver representations. D is diagonal matrix with entries dk, and theta is just vector theta K's. And then we have a global basis independent multiplicity matrix that just counts how many times target hits weight space K minus how many times source hits space K. So with all that defined, we have our main results, which is Harder-Narasimhan filtration for hyperquiver representation. So suppose phi is theta unstable, it's an unstable point. Then there exists a unique admissible Q filtration F called the Harder-Narasimhan filtration, such that it is uniquely defined by the following two properties. So the one is our normalization condition, and the second is that the associated gradient representation is semi-stable. But semi-stable not for theta, but for some shifted parameters, which we call theta tilde. And this is for the action of the Levy subgroup associated to this filtration. And this kind of shift is something you often see in applied AGGITATE. So these are two defining conditions for the agent filtration, which makes it unique. And furthermore, it has a decreasing sequence of rational weights L1 up to Ln, and you can write a formula for the weights, which is given in this equation. So the matrix L here is this some sort of Laplacian matrix, and L dagger is the pseudo. So this gives us a formula for the weights, and you can see that unlike the quiver case, you need information about how the graded associated gradient splits, which you did need for. So what can we do with this theorem? Well, the first thing to notice is that this is our formula for the weights, and if we go back to quiver representations, you can show that by using this complementary slackness condition for the KKT condition, that in fact this A matrix is 0, and the formula reduces to L equals some scale times D inverse theta, which if you write component wise, you actually see that it's up to scaling the same as the slope of the successive quotients in the HN filtration. So these weights you can therefore think of as generalized slopes for further representation. Another thing you can do is look at certain hyperquivers. So Jones had this result. If you pick a positive stability term with the theta, then the finite dimensional associated algebra is theta semi-stable. If and only if it is semi-simple as an algebra. And semi-simple means that it has no non-zero nilpotent ideas. And Jones's proof used the Barton-Weider-Ring theorem to embed the algebra into a matrix algebra. It uses some machinery, but you can in fact find a simpler proof just by using the weights profile. So the weights can tell you what the connection is between semi-stability and semi-simplicity for these kind of algebras or algebra-like objects. So what one can do this is like what I said. So hyperquiver representations, they encode all sorts of structures that resemble algebras but are more general. And one thing one can do is to use the weights formula to connect GIT semi-stability of these representations with notions of semi-simplicity. So, for example, can we do this with bialgebras or hot algebras? This is something which one could work on. And one can also study representations of these internally graded unipotent groups, which show up in non-reductive GIT, and one can ask how much can we say about these representations, and therefore how much can we say about moduli of unstable objects. And another thing one can do is what is this connection with Laplacians? So there's this matrix L that showed up in the formula, which you can see as some sort of Laplacian of a weighted hypergraph. And so it would be interesting to know how much further the analogy goes of hyperquiver representations. And maybe you could say anything else about GIT. So that's what I have to present, and thank you both.
We have questions for Tommi.
Is it possible to do that maybe just to work over positive characters? Kind of talks and what they would see, and at some point you're dividing by two, so maybe more characters.
So actually, I think it is possible. There's definitely ways in which you can generalize all of this. So Kemp's original paper about instability, he worked over a perfect field, I believe. So it doesn't have to be characteristic zero. So I think results like the HKKN stratification or the HN filtration for hyperquivers, I think that should work over a more general field than C. But I think what you might need the complex numbers for is if you want to connect it to, let's say, more spheres. How does the HKKN stratification compare with the more stratification under the moment map that you might need complex numbers for? But also, Jones doesn't required steaming. So actually, Jones's result about semi-stable economic, semi-simple it works for algebras of again perfect figures. So I think that can work. And I guess there was a two somewhere here. Yes. So this is not actually that important. We don't actually need this two. The two is just to
In the real anyway.
sorry.
In the real anyway.
Oh, yeah, it's.
Yeah. Well, but yeah.
Yeah, nothing.
It's just your length, so.
Any further questions?
Yes.
With the rope theory, you have finite type quivers. I guess are there any hyperquiver ropes that are finite type that aren't quiver ropes?
But finite type.
Finite rope type, sorry.
As in like finite type versus tame versus
Yeah.
Oh, yeah. This is not something I've looked into, but that's a very interesting question. Yeah, definitely. At first I thought you were saying are there finitely many Harder-Narasimhan types, but there are, but that's definitely an interesting question. Yeah, I don't know. Okay, put it into account.
Were there any more questions?
If not, let's thank Tommy again.